Okay, so welcome back. Now, what we have done so far is we have now solved this Stokes' second problem. Remember, the question was, we have a wall that is oscillating back and forth with a certain angular frequency of omega. We have solved that by essentially doing an ansatz with complex harmonic functions, so sines and cosines, which eventually leads to a separation of variables. And then we have found, at the end of the day, we have found this result here. U of y and t is v times e to the minus ky times cosine of omega t minus ky. Maybe it's important to remember what k actually was. K was the square root of omega divided by 2 nu. So that means that the omega and in particular the viscosity goes into the k, but it's a constant. It's not something that changes as a function of y or as a function of t. It's a constant. So that means we can now identify a number of different parts of our solution. We have certainly this first part here, which is v times e to the minus ky. This is something that is essentially, we can assume that this is, or we can say that this is a damping as a function of damping in the vertical direction y. Then we have a second part here, this cosine, where we have a balance, or we have the cosine as a function of omega t minus ky. And of course, this is something that you probably all know, but we will look at it now in more detail. This is a propagating wave in both y and t. So that means the solution that we have now obtained has actually two different components which are multiplied with each other. On one hand, we have a damping in the vertical directions, this e to the minus iky, and then we have something that is just propagating. It's a cosine, so that means it's always between 1 and -1, so that the amplitude will not change. It will just kind of move in space. That's what I would like to just show you.
Professor.
Yeah.
Excuse me. I don't get how you get the general solution of the problem Fy. Down.
Here.
Yes. That one.
This one.
Yes.
Okay. So let me explain that again. So we have obtained that at this point we have obtained the ODE f double prime minus I omega divided by nu times f. Now we realize at this point that this is an ODE with constant coefficients, because I omega divided by nu, that's a constant. That's not part of the solution, or it's not a function of the solution. So that means we essentially can make an ansatz in this form here. So this f is c times e to the lambda times y. Why can we do that? Well, because we see that essentially this ODE says that f double prime equals I omega nu times f. So the functional form of the second derivative needs to be the same as the zeroth derivative. And of course, one typical, or one function where derivatives are the same as the original function is, of course, the exponential. So that means if I'm making an ansatz with an exponential, of course, I will know that the zeroth derivative and the second derivative will have the same functional form, this I lambda y. What then remains to be seen is what this c constant would be. And this is exactly what I can calculate now from here. If I put in f and f double prime into this ODE, I mean, I can quickly do that just to show it. So, I put in c lambda squared e to the lambda y, that's the f double prime, minus I omega divided by nu times f, and f is c times e to the lambda lambda y. And if I do that, then I can see that this goes away, this goes away, this. So what is, of course, this needs to be 0. And what is remaining here is lambda squared minus I omega divided by nu is 0. That of course is exactly what is written here. This I can solve. I can take the square root, and then I get this lambda being plus minus of this. So that means the two solutions for lambda here are, you know, plus or minus the square root of I omega divided by nu. What I did here, this was just reformulating this square root of I to make it a little bit nicer, so that I get in the end that this lambda is k, which we introduced. Where did we introduce that? Here we introduced k, which is the square root of omega divided by nu times I plus 1. So this is then just my two lambdas. So that means I know now my solution needs to be composed of c times e to the lambda y with two different lambdas. And of course, because it's a linear ODE, the general solution would be the sum of these two solutions. So therefore, my general solution is then this one here and this one here. This one would be for the kind of the positive lambda. Positive lambda, I mean this sign here, and this would be for the negative lambda, so for the lambda with this sign here. And then, of course, if I put in, well, actually, I mean, it's here, so the plus and the minus. So this is the general solution. Then I would just put in the boundary conditions, and then after that, I will end up with this equation.
Okay,
thank you. Okay, yes, good. So now, so I would like to talk a little bit more about propagating waves, because I was just saying that this here is a propagating wave, but maybe it's not clear to everyone what I actually mean with a propagating wave. So it may be good to recap that very briefly. So a propagating wave means that at least I need to have a two-dimensional domain where I have an x. Well, I'm doing it now as a function of x, but of course it could be y, and then I have time here. Well, propagating means that I have something that moves inside this domain. And I would now say, okay, I have waves, which I show here with these red lines, and these red lines would actually correspond to wave crests. So when if you have a wave, if this is a wave, this would be the wave crests. So where you have the maxima. So these would correspond to the wave crests. So that means now what I mean with propagating, if I'm standing at a fixed location, and I will just wait and go forward in time, then I would see a first wave passing, then I would see a second wave passing, then at some point I would see a third wave passing. So that's what I mean with a propagating wave. So it kind of moves through the domain, and if I'm standing still, it is one wave coming by, next wave coming by, and so on. Now, using this graph here, I can, of course, read out a few interesting numbers. So, for instance, the distance between two wave crests, that would be the period. So this would be 2 pi divided by omega. And I can also look at the wavelength in space. So if I'm taking a picture and looking at the wave, then the distance between two crests at a given time would be the wavelength. So that would be L perhaps being 2 pi divided by K. K being the wave. And then the last thing that I can see from here is actually this angle or the inclination of the or the slope of the wave crests, and this would be the wave speed. Typically, denoted with the letter C. So if I'm just summarizing everything that I wrote in here, we have the wavelength, L being 2 pi divided by the wave number K. We have the period, T being 2 pi divided by omega. We have the wave speed. The wave speed being C, which is essentially the slope of these lines. And of course, now when I have the wavelength and the period, I can see that this is actually just omega divided by K. So this is for a propagating wave. The equation of what I have shown here is exactly what I had. This can be written as a cosine, as a cosine of let's say omega t minus k times x, which of course is the same because the cosine is an even function. This is the same as kx minus omega t. If I'm using the wave speed, I can also write this as the cosine of k times x minus ct. Of course, now you directly see why this is a speed. Well, it's a distance or a position minus ct, and ct, of course, is kind of if you have a constant speed times a time. That's of course the distance that has been taken with a certain time t. So this picture of a propagating wave can be expressed with these various cosine functions. And of course, if we compare this, what I have here for the propagating wave, cosine omega t minus k y, is of course exactly the same as I had here. So now for us, if we now talk about the wave speed, in our case, c omega divided by k, and if we now assume that this k is the square root of omega divided by 2 nu, this omega divided by k becomes 2 nu times omega. Now, what we still kind of need to understand is, what does this solution here really mean in our case of an oscillating wall of Stokes' second problem. So of course we have this damping in y, so that means it's kind of obvious that maybe our function becomes lower the further away you are. But still the question is, what is actually propagating? What is this propagation really meaning? Well, actually it means that this propagation means, or I can write it like this, the propagation of the vorticity at the wall into the domain. So what is propagating here is actually the vorticity at the wall, which of course changes because I'm oscillating back and forth. So how fast is this actually propagating upwards, away from the wall? Of course, the wave speed, or you could say with speed, of course, this speed is exactly this wave speed c. So the phase velocity of this wave into the domain. And it's not only propagating, because if it was only propagating, it would not decay. But while it is propagating upwards, this vorticity, it is also decaying with this e to the minus ky. So it's propagating with speed c, while decaying with damping, and it was e to the minus ky. So that's now our solution. We generate vorticity at the wall. This vorticity is propagating with a certain speed into the domain. And while it's doing so, it is decaying with a certain damping term. Of course, that means that we can now do a sketch of that, just without even looking at an animation or anything, just from knowing or from looking at this solution. Let me now try to do that. If you now plot here on this axis the velocity, and this axis we plot the vertical distance. So then we know that our velocity actually goes from plus or from minus v to plus v. It's kind of going back and forth here. I mean that's our oscillation. So, and then I said it's kind of a propagation into the domain which decays with this the damping rate. So I can just maybe indicate this damping. So this line here would be this v times e to the minus ky, and then the propagation would kind of look like this. So this is the cosine term that goes away from the wall into the domain. And of course, now we can measure also the wavelength. So if one wave crest here, another wave crest here. So this distance, this distance would now be L being 2 pi divided by K, for instance. Okay. And of course, now if I'm moving, so if I'm changing time, this point down here would kind of move back and forth, and as would now the vorticity or the velocity would propagate upwards with this particular speed, which we have indicated or identified as being c. Okay. So as before, as for the Stokes first problem, we can now think a little bit about vorticity and viscosity, what the effect of that is. And then we can again talk about the boundary layer thickness. And at the end, I would also like to show you how this solution actually looks like. So let's maybe first talk about the effect of viscosity. So the effect of viscosity here is, well, we kind of said it before, the viscosity is that part that actually makes it possible for a momentum to diffuse away. And now, of course, we have the problem because the momentum is oscillating. It, of course, means that also this oscillation is diffusing upwards. So we have momentum diffusion. And of course, this is part of the oscillation that we impose. So it's not, but it's in this case, it's not just diffusion, so that it's kind of propagating upwards. It's actually also that there's a damping. Of course, that means that there is a certain dissipation of mechanical energy being present. So we actually lose velocity, and of course we lose that to a temperature field, which you don't solve for, but essentially that's where the energy goes. So we transform mechanical energy into temperature And of course, this will show up as a loss, as a kind of a reduction of mechanical energy, essentially. And of course, this is exactly this damping term that we have in the equation. The decay rate we have calculated. That's exactly this k, which is omega divided by 2 nu. So I mean, that's the, you know, that's the. Oh, sorry. This is the decay rate. So the k is the in the exponential. And of course, now it's interesting to understand, yeah, how does this decay actually depend on the frequency? And if you look at it, you see that the decay is k, and the definition of k is omega, or the square root of omega divided by 2 nu. So that means if I have a higher frequency, so if I oscillate this wall extremely fast with a high frequency, so that means I actually have a large omega, that means my decay rate is actually faster with a higher decay, because my k is larger. And of course, at the same way, if I have a lower frequency, I get a lower decay. So that means if my purpose is to diffuse as much vorticity or momentum from the wall far away, I should make sure that I'm not doing that with a high frequency. I would like to do that with a low frequency, like in Stokes' first problem, where essentially I have a frequency of 0 afterwards. Then everything will actually diffuse away. So that means for the lower decay, I have a more efficient momentum diffusion. Okay, so this was the effect of viscosity, or frequency, if you wish. The second point that I would like to mention before we look at the video, or before we look at MATLAB, is actually the effect on the boundary layer thickness. Because also here, if you have this oscillating wall, you can again kind of measure how far into the domain do I actually feel that the wall is moving. Because it's clear, if I'm far away, you know, the diffusion or the decay is so strong that I would never ever feel that there was this oscillation. And of course, this is what I could again define as the region which is affected by the wall movement. So the boundary layer, or the boundary layer thickness, is a measure for how thick is the affected region, or as we discussed earlier, how thick is the vortical region, so the region where I actually have vorticity being present. And of course, I can do now exactly the same thinking as I did in Stokes' first problem. So I again define a certain delta, where I say delta is the position, the y position, where the velocity u is on the order of, you know, let's say 1% of the amplitudes that I had at the wall. And of course, this essentially just relates to the damping term. You know, this essentially just depends on, you know, on this term here. I'll take away all of them. So I can directly write that just as a function of this exponential, something like that. E to the minus delta times k should be 0.01 or 1%. And of course, this I can solve. This is not difficult to solve as a function of k, which will then give me delta as the size of 4.6 times the square root of 2 nu divided by omega. Or if I want to use K, of course, 4.6 divided by K, or it's 6.5 times omega divided by K if you want to have the speed in there. I mean, it's all the same. Yeah. Okay. So this is now the thickness of my boundary layer, and so I just want to kind of give you an example so that you have an idea of what types of thicknesses we're really talking about. Let's assume we are in water. So let's assume you have I don't know, you're in a pool of water, and you move a wall with 1 hertz. So back and forth with 1 every second. How thick is this boundary layer? So how far away from the wall do I feel the movement of this wall? So and the definition was that the decay is or the velocity has this decayed to 1%. So think of water with 1 hertz, so something like that. Actually, you can just calculate it. Take this formula here. You know the viscosity of water. The omega here is you have 1 hertz. Well, the result is, it's actually, I don't know whether this is surprising, but to me it was surprisingly low. It actually is just 1 centimeter. So, and above that much, your velocity has already dropped to more than, or by more than a factor of 100. I thought it would kind of be much thicker, but it's actually quite small, which also means that it's momentum diffusion with this oscillation is not a good way if you want to affect the whole domain. Of course, now we can also look at air, just to give you kind of the comparison. Again, we do air with the same frequency. So now you can wonder, is this more or less? Of course, we can go back and calculate or we can use the vorticity, and it actually turns out that the air delta is 3 centimeters. So if I'm doing that here, I could measure the velocity here. I would feel it up to 3 centimeters away from my moving wall or my moving hand. Of course, now you can wonder, okay, this is all very good, and oscillating walls are not relevant. It's just kind of a problem to show that you could use complex functions to solve problems in fluid mechanics, which of course is true. But actually, it turns out that there is a very obvious, or not, maybe not obvious, but a very practical application, and that is actually used in engineering fluid mechanics. It's actually an application to what we would call flow control. Well, what is flow control? Flow control is the idea that if you have a boundary layer flow, so for instance the flow around a car or an airplane or a wing or something, you would like to control it, meaning you would like to, for instance, reduce the drag or minimize the drag, or something like that. And oscillating walls that go back and forth, they have actually shown to directly affect what is called the near wall cycle of turbulence. So the way that a turbulent boundary layer is regenerating it and kind of leading to sustained turbulence. So that means that we can use oscillating walls to actually control, to affect the drag that is exerted of a boundary layer onto a body, like a car or a wing. The idea is that it's like done like this. If you have a plate here, something like that, you have a flow coming. So this could be a car or something. And then you have a region here inside this plate that goes back and forth, as we just discussed. Then it actually turns out that you will reduce the drag. You will reduce the drag that this plate would experience. So you would actually need less power to move this plate through the flow. And of course, that's kind of an interesting application, because if you just look at the streamline now, this streamline maybe will kind of move like this, and then later on it would move like this. So it would go back and forth. Of course, now one question that you may ask if you have this this situation is, how far above the plate, so now in the vertical direction, this is the y direction. So how far up do I feel this oscillation? And of course, the answer is exactly this one here. So we know now from just this very simple, I mean, from this analysis, I can estimate how thick, how far up I would actually feel this oscillation. And this is actually called a Stokes layer, because this is actually a solution of Stokes' second problem. So if you have the boundary layer above an oscillating surface, this is called a Stokes layer. And we can now estimate the properties of that using what we have calculated today. So the last thing that I would like to show you today is actually a code or a small MATLAB script that I have written to just show you how the solution would look like. I will also post it afterwards online. So I guess I have to share here the screen like this. So if everything goes well, you should be able to see my MATLAB window. Do you? Yeah.
Yes.
Good. Okay. So this is a very simple code, and I hope I can make it a bit bigger. I think I need to press like this. Okay, I don't know how to make it bigger now, but that's maybe not such a big problem. Essentially, it's a simple MATLAB script, which I just define a few values for the omega, for the velocity, and for the viscosity. I mean, I just took some values. It doesn't really matter. And then I calculate in a specific domain. I calculate numerically the solution, and then I plot it down here. I guess the easiest if I just show it, I let it run, and essentially this here is the solution that I get. So down here at y times k being 0, I have my wall that moves back and forth, and then I see exactly this oscillation that I tried to sketch before. So this propagating wave that propagates upwards into the domain. And I have here the green dashed line, which is this the envelope, kind of the decay. And here with this vertical, with this horizontal line, I also indicate the boundary layer thickness. So the point where I have reached 1% of the amplitude down here. And this here would now be the velocity field in a Stokes layer. It would just go back and forth and back and forth. So this is now the exact solution of Stokes' second problem, as we have derived today. Okay, I guess with this demonstration, I would actually like to close my discussion of Stokes' first and second problem, and in that sense also close the first part of our course, namely the exact solutions for certain viscous flow problems. So therefore, my question would be: do you have any questions or anything that is unclear or that we should discuss a little bit more? Because next time we will, which is on Tuesday, we will actually start with real boundary layers. So we would go into the boundary layer approximation or boundary layer theory, which goes back to Ludwig Prandtl in the beginning of the 20th century. And we will then derive the various, Blasius boundary layers and so on. And of course, that will be quite an interesting part of the course. And as I said, next week on Tuesday, we will have an online lecture as today. And then Thursday and Friday and Monday, I will hopefully be in Bologna or in Forlì, and then we can do the lecture together in the classroom, which of course is kind of nicer, of course, because then we can also talk a little bit. Okay, if there is no more questions about the material for today, then I would actually like to stop for today, because we have now exactly reached the end of the first part, and then next time we start with the boundary layer theory. Okay, so thank you very much for today, and have a nice weekend, and we meet each other again next Tuesday. Thank you.
Bye, Professor.
Bye.